This is Unit 5, Investigation 1, Lessons 3 and 4. So we're going to be starting off with an entry ticket. That's going to be a little bit of review on factoring. We want to write all of these expressions in factored form. So remember, you have to multiply to the last term and add to the middle. And you always want to be on the lookout for any type of pattern you might see. So if you're here, I know that there's a greatest common factor, 3. So I know x times 3 will give me that 3x, and I know 4 times 3 will give me that 12. So this is my factored form. Down here, I'm just going to use that trick that we just spoke about. I know x times x is the only way to get x squared, and I know that 4 times 2 will give me 8, but 4 plus 2 will give me 6. Okay? Here for number 3, this is going to have to be x times x because that's the only way to get x squared. And here I know that 6 times 6 is 36. And here I have no middle term, so I'm going to have plus 6 minus 6 because 6 times negative 6 will give me that negative 36, but 6 plus that negative 6 will give me 0. Side note, we know that any perfect square in the form x squared minus a squared can be factored into the expression x minus a times x plus a, and we worked on that during our factoring unit. So just a little reminder there that if you didn't get this x plus 6, x minus 6, if you remembered that, that would have also gotten you to the same result. On number 4, we're going to move on and we're going to say, okay, well, I know these are all even numbers, 2, 2, and 12, so I can factor out a 2. So I know my x squared times 2 will give me my 2x squared. I know that plus x, so x times 2 is going to give me that 2x, and I know that negative 6 times 2 is going to give me that negative 12. Here, we just have to remind ourselves we're not done here because we still need to factor out the expression that's in the parentheses. So here, I'm going to have negative plus 3 and minus 2 because 3 times negative 2 gives me negative 6, but 3 plus negative 2 gives me that 1 in the middle. Moving on to the concept development, we're going to be looking at a function that's a little bit different than we're used to. It's in a different form. We're used to looking at a function that has a numerator and denominator with the same degree, because then we can get our horizontal asymptote really easily by dividing those coefficients. Here we have a denominator that has a greater degree than the numerator. So here we're going to fill out this table. You could have either used Desmos or directly computated it. We're dealing with some ugly numbers here, so it might have been easier to use Desmos. So the first thing I'm going to do is I'm going to set my denominator equal to 0 because I want to see my restrictions. And you're going to see that the restrictions are on 2 and negative 2. So that means I'm going to have an asymptote at those two lines. That is going to give me my domain, which is going to tell me that negative infinity to negative 2, union negative 2 to 2, union 2 to infinity is my domain because it includes absolutely every value of x except for the values 2 and negative 2. So that's actually also going to give us our vertical asymptotes and there is 2 because we have 2 values that x cannot be because those 2 values will give me undefined solutions. So here now we're going to figure out our x and y intercepts. So you're going to find that there is no x-intercept, but there is a y-intercept, 0, negative 0.25. And now we're going to figure out, okay, well, looking at my graph, as x is approaching negative 10,000 or 10,000, what is y doing? So you could actually look at your table here as well and see that they're getting considerably smaller, or you could have graphed it in Desmos and looked at it at that on the graph here. So as you can see, as x is getting larger, it's going to the right, and it's going towards that 0 value. And the same thing happens if you're going to the left. If you're going to go towards that 0 value for y. So here, we're approaching 0 from either direction, and that's going to tell us that we have a horizontal asymptote at y is equal to 0. That's also going to tell us our end behavior, right? So as x is going towards infinity, or if it's going towards negative infinity, either way, your y is heading towards 0, which does make sense because our asymptote is y is equal to 0. Here I made a little rough sketch, but you feel free to use Desmos so you don't have to graph it. On the next page, number 2 is a very similar function. We have 2 over x squared minus 9. Again, we have a denominator that's going to be greater than our numerator degree. So here we're going to fill out this table. You could have also graphed it in Desmos, but we'll look at that in just a second. The first order of business I need to do is I need to figure out what restrictions are on my x value. Well, my x squared minus 9 is a perfect square. So if I factor that, I know it's going to be equal to x minus 3 times x plus 3. So in that case, then my restrictions would be on 3 and negative 3. So given that, I know my domain is going to be negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. Notice that there's all parentheses because it is not inclusive of the values 3 and negative 3. From either the table or from the graph, you would have seen that your x and y intercepts are as such. There is no x-intercept, and the y-intercept is 0, negative 0.2222. So again, not the prettiest number to be working with, so that's why I would have done this in Desmos. From here, we're going to actually go to our graph, and it's going to ask us, okay, well, as x is approaching negative 10,000 or 10,000, what is your y value doing? So you actually can reference your table here too. So if you look on the left here, if you look at the 10,000, negative 10,000 value, you have 2 times 10 to the 8th, and over here you have 10,000, and you have the same value over here. So we want to know, well, what's happening here? So if I go to my graph, here, and it's wondering, okay, well, if I'm going essentially towards negative infinity or positive infinity, what's happening to my y value? So here, if I go to the left, I'm going towards negative infinity, and it's going closer and closer to that 0 value. And the same thing happens over here if I go to the positive infinity from the right. So that's going to tell me that y is equal to 0 is actually my asymptote. And again, that's going to be a dashed line because it is not inclusive of the function. So here that tells us that as we go to negative 10,000 or 10,000, we are approaching 0. And our horizontal asymptote, y is equal to 0. And again, just to reiterate, the negative 10,000 is essentially saying negative infinity. The positive 10,000 is like essentially saying positive infinity. So our end behavior, it's asking, well, as x is getting really large or really big, what's happening to it? Well, it's going towards 0 either direction, which does make sense with our asymptote because we have y is equal to 0 as an asymptote. So here I did a little rough sketch of the graph, but again, you also have Desmos to do this, so you don't have to do it by hand. And actually up here, this should be a negative value. Moving on to page 47, we're doing the entry ticket for lesson 4. Notice that we're working with yet another function that has a denominator with a degree higher than the numerator degree. So here, the first thing I want to do is I want to solve for my vertical asymptotes. I know that whatever values my x cannot equal, then that has to be my asymptote. So here, if x minus 3, then what value would make that 0? Well, 3. So I know I'm going to have an asymptote at 3, and I know I'm going to have an asymptote at negative 2, because negative 2 plus 2 would give me another 0 on the denominator. So that's going to make my function undefined. So here, my restrictions are on x is equal to 3 and x is equal to negative 2. So if you draw that on your graph, it's going to be a dashed line because it's not inclusive of your function. Now, I'm going to jump down to my domain because now that I know my restrictions and I'm dealing with my x values right now, I'm going to deal with what my domain should be. So again, you need to have this in interval notation, and I'm going to account for any value that's not negative 2 and not 3. So here I have negative infinity to negative 2, union negative 2 to 3, union 3 to infinity. So now I'm going to actually graph my function. If I go to Desmos here, this is what it's going to look like. And now I got to try to figure out, okay, well, I know my vertical asymptotes, but what is my horizontal asymptote? So I know that I have x is equal to 3 and x is equal to negative 2. Again, these are going to be dashed lines. And if I look here closely, I actually am going to see that, okay, well, the only other limitation seems to be around this area, which is going to be at y is equal to 0. But what doesn't make sense is, okay, well, there's an intersection. So we're going to think about that for a second. So here, if you graph, you're going to put a little rough sketch of your graph up, and you're going to put up that your horizontal asymptote looks like it's going to be y is equal to 0. And you can actually double check, because if you look here, all right, well, let's look at our limitations, right? So as x is getting really large, going to the right, it's going towards 0. as x is getting really, really small, going to the left towards negative infinity, the same thing happens. So we should have an asymptote at y is equal to 0. And again, that's going to be a dashed line. So as you can see, we had that really weird point of intersection in the middle. So that's going to tell us that, well, 0, 0 is both our x and our y intercept because it's 0, 0. It's the origin. Technically, it's actually neither, but that's the only point of intersection. So we're going to have to write that as both the x and the y intercept. And lastly, we kind of want to get thinking a little bit more about this, okay? If we know that y is equal to 0, what is wrong? What seems kind of odd? Well, our intersection at 0, 0. Well, if we are dealing with an asymptote and our asymptote isn't part of the function because it's what our function is limited to, then how can there be an intersection? So we're going to be kind of thinking about that and coming to some sort of conclusion together as a class. The next page, we're doing the concept development for lesson 4. So we already kind of spoke about how we just saw there was an intersection on our asymptote, and we didn't think that was possible. So we might need to adjust our definition of a horizontal asymptote for right now. And right now we're just going to consider this function, which does have a horizontal asymptote at y is equal to 0. So they give you that. What it's saying, though, is to determine if a function's graph crosses its horizontal asymptote, there is a way for us to compute that. We just need an input A that has an output B, where like your g of A, which is your function in terms of A, is equal to B, which in turn tells you your y value, your y is equal to B as the horizontal asymptote. So here we're just going to test that out a little bit. I know that here I can actually solve for my vertical asymptote. That part's easy. All I need to do is just set the denominator equal to 0. If I set each of those factors equal to 0, I can see that my vertical asymptotes are going to be x is equal to -3 and x is going to be equal to 1/2 because those are my two restrictions. They give us our horizontal asymptote already, but I'm more worried about the math that let them give us this as our horizontal asymptote, which is what that little blurb we just read was saying. So here I have to figure out, well, where is my numerator equal to 0? It's basically telling me to find out where there is a cross on the horizontal asymptote. We need to see where there is an input A that has the output B. And if B is 0, because that's the value they're giving us, then when is this function equal to 0? And I don't really care about the denominator. I know my denominator can't be 0. That would be undefined. So if I want to know what makes this function equal to 0, all I need to know is what makes the numerator 0. So I'm going to set the numerator equal to 0. And here you can actually divide by 3 on both sides just to get the x plus 4 alone. Then you can subtract 4 on either side to get x is equal to -4. So because x is equal to -4, that's going to tell you that at -4, 0, that is going to be where you're going to have a cross on your horizontal asymptote. In Desmos, as well as my 3 asymptotes, you can see my dashed lines are my asymptotes, and my green line is my function, my rational function. So here, if you look at the graph, you can see that the asymptotes, the function's going towards the asymptotes, not touching them, but if you look and you're kind of clicking through some of these critical points on the green lines, you're going to see that here on our asymptote y is equal to 0, we have an intersection with our function at -4, 0. So you can actually look at that and get that from your graph as well, not just algebraically. On the next page, we're going to continue, and there's another function they're asking us to work with, r of x. And here, this might look like a really complicated function, but I don't want you to get too overwhelmed yet, because if you look, well, I have 2 x's in my numerator that I have to multiply against each other. So my degree on my numerator should be x to the 2nd power. If I look on my denominator, I have 3x times x, so that's going to actually give me also a degree 2 on my denominator. So here, the first thing that I'm actually going to do is I'm going to multiply this out just to double check. So first I'm going to distribute on the numerator. I'm distributing in. On the next page, we're continuing on with our concept development. So we're going to be working with the function r of x as seen right here. And we want to know if there's a point where the graph of the function crosses its horizontal asymptote. So we want to answer what we just did above. But before we do that, let's actually just do a little bit of algebra. If I distribute these factors, I have 2 times x plus 3. I'm distributing that 2 in first. I'm going to get 2x plus 6, and then I have to multiply that expression by that x minus 2 expression on the numerator. So far all I did was just distribute in that 2 value, and now I gotta do some FOIL, right? So I gotta make sure that I'm multiplying all my values properly, and then I'm gonna be simplifying to this expression. So I have 2x squared plus 2x minus 12 all over 3x squared plus 10x minus 8. So that's just what we get from distributing and simplifying both expressions. Now, this is where the powers kind of come into play that we were talking about at first. So if you notice, we have 2x squared and 3x squared as our 2 leading terms. So if we actually remember, if we have the same degree, numerator and denominator, we actually can find the horizontal asymptote really easily just by dividing those terms. So I like to make sure that I keep the term with the whole entire term when I'm doing this, because it's just another reminder that if my numerator and denominator don't have the same degree, then they're not going to be able to neutralize and create 1. Okay, so x squared over x squared is going to neutralize and is going to give me that 2/3. So that's going to tell me that my horizontal asymptote is y is equal to 2/3, and you can write that right here. But now it asks us to find, okay, well, where on the graph does this function cross its
The last function we're going to be looking at today is going to be k of x, which is x squared plus 3x all over x plus 5. So here, if you did want to factor the numerator, which is not necessary for this, but if you did, you could have had x times x plus 3, and it would have been an equivalent function. So the first thing I want to do is I want to find my restriction on my x. So I need to figure out, okay, setting my denominator to 0, what is that restriction? Well, x plus 5 can't equal 0, so that means x can't equal -5. So that's going to be my vertical asymptote. And again, if you're going to draw that, you got to make sure that it's going to be a dashed line. Now for the horizontal asymptote, so we've kind of been working with functions that have the same degree, numerator and denominator, and we know that we can solve for the horizontal asymptote by dividing those coefficients, those leading coefficients, but that's only for when they have the same degree. We've also worked with the past 4 functions, having an example where the denominator is larger than the numerator. The degree of the denominator is larger than the numerator. So in that case, our asymptote always seems to have been y is equal to 0. Now, I just want to touch on this type of example, because this is what we're going to be doing a lot of next class. So here, we're looking at, okay, let's see what this even looks like. Let's graph this in Desmos, and if you look, it's kind of slanty looking. We haven't really seen a function like this really before. I'm not really sure where I'm supposed to be looking or what value the 2 functions are supposed to be going towards, but I know a trick, so I'm going to teach that to you. So now, whenever you have a numerator with a degree n and a denominator with a degree m, if your n degree is equal to your m degree plus 1, which is the same thing as saying if your numerator is 1 degree higher than your denominator, then you're just going to have to divide the numerator into the denominator and solve for what's called a slant asymptote. So that's what we're going to do here. We're going to solve for our slant asymptote. If you do the long division out, you're going to end up with x minus 2 with the remainder of 10 over x plus 5. So here, what's actually really interesting is, you know, when you get to bigger and bigger values, your remainder doesn't really matter. It doesn't really have that big of a impact. So here, the remainder doesn't matter, and the quotient is what we're using for our slant asymptote. So now if I go to Desmos and I'm going to graph this slant asymptote, I'm going to have y is equal to x minus 2. And that's going to be a dashed line because it's an asymptote. Instead of having a horizontal or a vertical asymptote, as you can see, this is a slant, so it's kind of sideways, okay? So here, it doesn't look like we normally have seen, but this is how you get a slant asymptote. This is how you get your limitation when you're dealing with a function, a rational function, where the numerator is, like I said, 1 degree higher than your denominator. So here, we're actually going to look for x and y intercepts, and here you can just look at the graph for that. You can touch your blue line and it'll tell you your critical points. It'll tell you your x-intercept is -3, 0, and your y-intercept is going to have to be left at 0, 0, because there's nothing else that crosses the y-axis. And now I kind of want to talk about my domain, and I want to include all the restrictions that I have here. So I know that my domain cannot include -5, but if you kind of see here, it does include -3, and it does include 0, 0. So what I'm going to do for a domain here is I'm going to say, okay, I'm going to have any number from -infinity to -3, union -3 to -5, union -5 to infinity. So this is accounting for not only just my restriction on my vertical asymptote, but it's actually also accounting for the value that 0 is included, and so is -3. So because of that, I actually made a mistake. So I'm going to take this, I'm going to take the parentheses away, and I'm actually going to add brackets because -3 is included.